In this section, Section 3.7.8 of Domain 3, we'll be focusing on fault injection within the context of security, architecture, and engineering. Fault injection is a key technique used to test the stability and security of systems by intentionally introducing faults to observe how the system behaves under stress. Understanding this technique not only helps in identifying potential vulnerabilities, but also in improving the overall resilience of software and systems. This skill is particularly relevant for the CISSP certification, as it directly impacts an organization's ability to preemptively address weaknesses before they can be exploited. By mastering fault injection, you'll be better equipped to ensure the robustness of the systems you oversee. In this section, we'll explore an important concept in the realm of security architecture and engineering: fault injection. Fault injection is a method used to test a system's behavior under adverse conditions by intentionally introducing errors or faults. This technique is highly relevant to the CISSP certification, as it emphasizes the proactive identification of vulnerabilities within a system. By understanding and implementing fault injection, we can enhance both software and system resilience, ensuring robustness against potential threats and failures. Fault injection is a method used to intentionally introduce errors or faults into a system. This technique is designed to test how the system behaves under adverse conditions, ensuring that any potential vulnerabilities are identified and addressed proactively. There are two main types of fault injection: software fault injection, SFI, and hardware fault injection, HFI. SFI targets the software layer and introduces faults into the code to observe the system's reaction. This helps in assessing the software's resilience and robustness. On the other hand, HFI focuses on the hardware components, testing the physical aspects of the system for potential weaknesses. By using both SFI and HFI, professionals can gain comprehensive insights into the system's strengths and vulnerabilities. This proactive approach is essential in enhancing the overall resilience of software and hardware systems, ultimately leading to more secure and reliable solutions. On this slide, we're looking at the relevance of fault injection to cryptanalytic attacks. The primary purpose here is to test the robustness of cryptographic systems. By introducing faults intentionally, we can identify potential weaknesses and failure points in these systems. Applications of these tests are vast, but the main goal is to ensure the confidentiality, integrity, and availability of data. It's also a way to safeguard against potential fault-based attacks, which could otherwise exploit vulnerabilities in your cryptographic defenses. The current slide focuses on software fault injection, SFI, an essential technique in testing the robustness of cryptographic systems by introducing and analyzing potential faults within software. Two primary techniques used in SFI include boundary value testing and fuzz testing. Boundary value testing examines the behavior of a system at the extreme boundaries of input ranges, ensuring that it can handle edge cases effectively. Fuzz testing involves generating random input data to identify unexpected vulnerabilities or weaknesses. An example of fuzz testing is using the tool Redamsa. With the command Redamsa original input file, fuzzed output file, Redamsa takes an original input file and manipulates it to produce fuzzed output files, which can then be used to uncover hidden bugs or vulnerabilities in the software. Overall, software fault injection is a critical methodology for ensuring the confidentiality, integrity, and availability of data in cryptographic systems by safeguarding against potential software faults. In this slide, we're focusing on hardware fault injection, HFI methods. HFI is a technique where we induce faults by manipulating the hardware environment in which the system operates. There are several ways to achieve this, including methods like electromagnetic interference, EMI, and power glitching. Electromagnetic interference involves exposing the hardware to electromagnetic fields, which can disrupt normal operation and help identify vulnerabilities. Power glitching, on the other hand, works by manipulating the power supply. For instance, rapidly changing the voltage supplied to a smart card can induce errors, making it an effective method for testing the card's robustness. The example provided demonstrates how voltage glitching applies rapid voltage changes to push the system into error states, revealing weaknesses. Understanding these methods allows us to simulate potential hardware faults that could occur in real-world scenarios and therefore develop more resilient systems. When it comes to fault injection tools, we have a variety of options both in hardware and software. Popular hardware tools include heavy-ion microprobes and laser fault injection, which allow precise manipulation and observation of faults at a micro level. On the software side, tools like AFL, American Fuzzy Lop, and Redamza are commonly used. For instance, running AFL for fuzz testing is straightforward. You'd use a command like bash AFL fuzz -I input dir -O output dir target binary. This command will initiate fuzz testing on your target binary using input and output directories to manage test cases and results. Understanding and using these tools and techniques ensures that you can rigorously test and improve the robustness of your application against potential faults. In this slide, we're focusing on the practical application of fault injection tools. To achieve the best outcomes, it's essential to integrate fault injection strategies into your software development lifecycle, SDLC. This ensures that faults are identified and mitigated early, enhancing system robustness. Regular use of fault injection during system updates is another best practice. By continuously testing, you can catch new vulnerabilities introduced by modification. Let's look at a specific scenario: testing the robustness of an encryption module. Fault injection can help ensure that the module remains secure even when subjected to faults, preventing the leakage of sensitive data. Employ these practices to maintain the integrity and security of your systems. Let's explore some real-world examples of fault injection. In our case studies, we'll look at how fault injection has been applied to cryptographic chips and tokens. Specifically, we'll analyze fault attacks on these hardware cryptographic tokens to see how they respond to various stress conditions like electromagnetic interference, EMI, and power glitches. A significant outcome from these case studies is the improvement in the chip's resistance to such disruptions. By subjecting these systems to rigorous fault injections, developers were able to identify vulnerabilities and enhance the robustness of their cryptographic modules, ensuring better protection of sensitive data. These examples underline the importance of fault injection in the realm of cryptography and demonstrate how applying these techniques can lead to tangible security enhancements. In this slide, we'll summarize the key points from our exploration of fault injection in cryptographic systems. First, we discussed the importance of fault injection testing in ensuring the security and robustness of cryptographic systems. This practice is vital as it helps identify vulnerabilities that could be exploited in real-world attacks. Next, we covered various techniques and tools utilized in fault injection. These methods are essential for simulating potential threats and evaluating system responses effectively. Lastly, we looked into real-world applications, highlighting best practices. Our case studies demonstrated how targeted fault injection can lead to significant improvements, such as enhancing the resistance of cryptographic hardware to electromagnetic interference and power glitches. These key takeaways emphasize the role of fault injection in maintaining the integrity and security of cryptographic systems, making it an indispensable part of security testing. In this final slide, we draw our conclusions and recommendations regarding fault injection in cryptographic systems. We've established that fault injection is integral for ensuring system security, as it helps in identifying and mitigating vulnerabilities. Regular testing not only enhances the robustness of your system, but is also essential for maintaining a secure environment. Moving forward, it is recommended to explore more advanced fault injection methods and to keep updating your skills through real-world fault injection scenarios. This will help you stay ahead of potential threats and ensure the continual security of your systems. In this slide, we provide valuable references and further reading materials to deepen your understanding of fault injection and system security. First, Security Engineering by Ross Anderson is an essential read, offering comprehensive knowledge on securing complex systems. Next, the National Institute of Standards and Technology, NIST Publications are highly recommended for their authoritative standards and guidelines in cybersecurity. Additionally, exploring online tools and repositories for fault injection practices can greatly enhance your practical skills. These resources will solidify your foundation and keep you updated in the ever-evolving field of system security.